Welcome back, everybody, to Bennett's Chemistry 12 tutorials. For those of you who are just tuning in right now, maybe to get some help with hydrolysis, this channel is actually specifically designed for the British Columbia Chemistry 12 curriculum. And not only that, but the first video starts at the beginning of the acid-base unit. And the intention is to do a series of lectures all the way through to the end of the year, anticipating that because of the COVID pandemic that we're probably not going back to school, which means that people are struggling to find ways of getting actual detailed instruction on the topics that they're doing, specifically in Chemistry 12. And because oftentimes when you Google something, or you go to Khan Academy, or you go to other sites, oftentimes it doesn't necessarily hit exactly what you do in your jurisdiction or in your school district. So this one's designed the way that I teach Chemistry 12. I'm a Chemistry 12 teacher in British Columbia, and so I'm making my series of videos specific to the way that I teach Chemistry 12 here in BC, kind of following the guidelines of the BC curriculum. Now, obviously, different teachers emphasize different parts of the curriculum a little bit more than others do. We all touch on everything that I'm going to talk about. We all touch on all of it because it's part of our provincial curriculum. But the unit that, say, I'm starting right now, the hydrolysis unit, some teachers keep it very specific to when they actually embed it into the titration unit, because it's designed as you need to learn things about hydrolysis of salts when you're trying to explain certain properties or characteristics of different types of titration. So that's how it's involved. I like to expand it a little bit more. I find it interesting. I find you can do a lot of things in the lab with it. It's got some practical applications to it, as you're going to see kind of later on. And so I kind of build it out a little bit more. I tend to keep it very qualitative. I don't necessarily do a lot of quantitative, but you can do very quantitative things. You can calculate pHs, and you can do a whole bunch of calculation stuff as well. So I'm going to focus this unit, I'm going to focus mostly on the qualitative aspects of hydrolysis, and less on the quantitative. And if your teacher wants to do the quantitative, you'll have to, I guess, meld what I talk about here in hydrolysis with particularly the weak acids and weak bases that you learned and amphiprotic species that you learned in the previous number of episodes that I did on acid and base. So that's the general framework of what I'm doing here. So hydrolysis for me is going to take me about 4 lectures here. So kind of check back in depending on what the topic is, and you'll see what we're doing. So the first video in the series on hydrolysis is going to be more of a general overview of the types of things that we're going to be looking at. Then it digs deeper and deeper and deeper and deeper into it. So you can see in the list of things that I've got here over my shoulder that we'll obviously talk about the definition of what is hydrolysis in the very first place. A general understanding of what types of things that we're going to be talking about. Not that hydrolysis is going to be limited out there in the real world of chemistry to what we talk about in Chem 12. But when we're talking about Chem 12, there are certain chemicals that we actually talk about specifically. So we'll make sure that I identify those types of things. And then last but not least, there's kind of a general strategy when someone's asking you, or you're trying to problem solve, or there's a practical scenario that you're trying to deal with. There's a general strategy for the decision making and the problem solving that you do with these things. And you'll see later on, I'm going to have flow charts out, and there's going to be, does this happen? Yes, no. And if it's yes, you do this. And if it's no, you do this. And then you go on, you ask the next question. And it's like a decision-making tree. And you'll see I'll have one of those out. doesn't mean you necessarily need to write it down all the time, but it's kind of this thought process that you go through in your head as you're trying to decide, okay, so if I dissolve this ionic compound into water, will it produce an acidic or basic or neutral solution? What will it do? Why do they use calcium oxide as lime when they spread it all over a lawn to kill moss? Like, why is that? What is the chemistry behind all of that? So you'll be able to, in your head, be able to go through this series of questions and actually determine, okay, well, this chemical is going to end up being produce a slightly basic solution, and therefore this is why it's used in this capacity. And that's the intention of this unit. And that's kind of why I like to build it out a little bit more, so that you can start to see things out there in the world from a practical perspective, why they're being used and things of that nature. Okay, so let's start with the definition of what hydrolysis is. So it's over my shoulder over here. So hydrolysis is a process. It's a chemical process. So you'll hear that word in various contexts, I guess the other sciences as well, particularly biology, obviously, where you might hear the word hydrolysis. And from a chemical perspective, we're just talking about a chemical reaction where water is one of the chemical reactants. So you've probably seen some. I mean, the Bronsted-Lowry equations that we used in the last unit, when you take a weak base and throw it into water, well, it reacts with the water. So that's, I guess, technically a form of hydrolysis, because it's a chemical process where water is one of the reactants. It's not just the solvent. Okay, so actual reactant, not just a solvent. And so that's kind of the first thing. I've given you an example to go along with that definition, and you can see that there's two reactants up there. One's calcium oxide and the other's water, and they form calcium hydroxide. So it's not just calcium oxide is dissolving in water to form an aqueous solution of calcium oxide. It actually chemically reacts and the bonding changes, and there's a new structure to the actual molecule. So that will happen in all of these hydrolysis things that we're talking about. Now, having said that, we're not going to look at the hydrolysis of all chemicals out there in the world. That would be too many for now, but understanding the general principles behind it. So we're starting with certain categories of things to introduce the concept to you. Now, these are some important ones, obviously. These are the big ones that you're going to be talking about in any kind of sense of hydrolysis. These will be the big ones. So category number one, and the one that you're going to do the bulk of your work in the hydrolysis unit, and later on when you start doing titration as well, is the soluble ionic compounds. So you take a cation and an anion, and they're formed into a solid crystal. So you've got gabillions of cations and gabillions of anions all kind of forming a solid ionic crystal. And you dump them into water. And I guess the question is, when you dissolve that ionic compound, that solid ionic compound into water, does it make the solution acidic? Does it make the solution basic? Or does it leave the solution as being neutral? And that's kind of the big overlying question of all of these things. So we're looking at soluble ionic compounds. And the reason why I've got the word soluble in there instead of just ionic compounds is to simplify issues, because if it was all ionic compounds, some dissolve better than others. So that just throws a bit of a wrench into the question of, does this make the solution acidic, basic, or neutral? Because sometimes a compound might be so bad at dissolving, okay, so really, really low soluble compound, that it produces barely any ions, and those ions barely do anything. So the question of, does it make it acidic, basic, or neutral? A little bit of a gray zone there, where you're uncertain because maybe the concentration's so low that for all intents and purposes it stays neutral, when in fact it should have been acidic. And so we're sticking with the soluble ones. So you throw them into water, and there's no question of whether or not the ions dissociate and start floating around in the water. Okay, so that's why the word soluble is there. So we're talking about soluble ionic compounds. Those soluble ionic compounds, there's limited ones. Okay, so there's the things that you're expected to know coming out of the solubility unit. Alkali metals are soluble with everything. Okay, so if an alkali metal is one of the cations, so lithium, sodium, potassium, etc., 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 If any of those are attached to an anion, you throw them into water, they dissociate 100%. You're expected to know that. The other one that you're expected to know is nitrate. Nitrate is an anion. It's NO3 negative 1. If you take any compound that has NO3 negative 1 as the anion, again, you throw it into water, it dissociates 100%. You're expected to know that. Ammonium is soluble with just about everything. So you're expected to know you take an ammonium compound, throw it into water, it dissociates 100%. And then there's a smattering of other ones, which of course the solubility table tells you if it's soluble or not, which, yes, we would expect you to know that. I mean, you've done that. That is expected, that you have that knowledge in your head. And you know that if you've got a weird compound, like you've got calcium sulfide, and you put it into water, is that soluble or not soluble? It's expected. We expect you as teachers. We expect you to be able to say, well, if I don't know if it's soluble at 25 degrees, I go to my table of solubilities and I try and determine if calcium sulfide is soluble. And then I look at the chart and I say, okay, so at 25 degrees it says it's soluble, it's not soluble. And what the definition of soluble actually means in terms of that 0.1 molar. So generally speaking, we're going to be giving you chemicals that are soluble ionic compounds, so you throw them into water. There's no question whether or not they dissociate into their ions. That should be a question that's removed from the equation of how do you figure these things out. So that's category number one. Category number two are chemicals known as anhydrides. And anhydrides are, for all intents and purposes, and I'm going to throw this out there, and you can nitpick later on when you go off to university and you get further into your chemistry career. They're also known as oftentimes oxides, and they become oxides because anhydride means removed water, or water is taken out. And so if you have a hydroxide compound, you can actually remove a water molecule and it leaves behind an oxide, and that's kind of how they can be made. And so that's where the two names come in. To keep it Chem 12 simplified version of things, we're talking about oxides. And so, like over my shoulder here, calcium oxide would be an example of an anhydride. Okay, so where it's just something attached to an oxygen. It doesn't necessarily have to be an anion of oxide. You can have a covalent oxide where it's covalently bonded to something, like carbon dioxide would be considered an oxide. Even though oxide is not an anion in there, and that's why the true name of the category is anhydride. So we'll get to those later, and you can see that I put later. We're not doing that today. That's going to be the last video of the hydrolysis series, will be about the anhydrides and what they do in water. And they're quite interesting because a lot of practical application and understanding environmental concerns and things of that nature all come from an understanding of the hydrolysis of the anhydrides. So that's the last class of the hydrolysis unit. Okay, so then we get down to number 3 down there, and we're talking about the dissociations of ionic compounds in particular. And the general strategy that you're going to go through in your head, you're kind of the step-by-step strategy, and I guess you don't have to do this. This is the methodology that I teach in my class. It's what I encourage students to try and go through. Of course, there's varying ways of doing this, and anytime you're trying to problem solve, I mean, really what your brain is doing is it's going through a series of checks and questions and trying to arrive at an answer. You're doing that. Some of you may take that pathway to it, and some of you may take this pathway to it. But you're going through that process. So I'm going to show you the process that I go through, that's kind of going through my head as I solve the problems that are presented to me with these ionic compounds, and trying to understand, do they hydrolyze and form an acidic basic, or do they leave the solution neutral? So what I want to do is I want to do this with I want to kind of demonstrate the concept with a generic concept, okay, so a generic ionic compound, and then I'll use a real one, and I'll show you just generally how it's going to play out. next class, as you can see, next class is going to be a way more detailed. It'll be much longer than this one is. It will be very detailed with the flowchart and the problem solving and the decision-making process that you make. And there will be many more examples of how you determine if you're getting an acidic, basic, or neutral solution. There's a whole bunch of things that you're going to learn that will complicate the issue, and we'll do that later. Now it's the general form. So let's pretend I have an ionic compound. Remember, we're talking about soluble ionic compounds, so assume that what I write down is a soluble ionic compound. So generic formula of an ionic compound would have a cation and an anion. So cation and anion, if I just call it AB, A is the cation, B is the anion. Okay, so they're connected to each other, and in any ionic compound formula, the cation goes on the left and the anion goes on the right. It's always how it's been. All ionic compounds are kind of the same way. That's the general strategy that everybody in chemistry has adopted. So I take that thing and I put it into water, and we're talking about the soluble ones, so they're dissociating 100%, and we'll always make that assumption, so you can just go ahead and do it at this point. So it dissociates into its two ions. But be very careful, because the generic kind of formula AB, all it tells you is it tells you the ratio that those ions are in. So if I put AB, it tells you that they're in a ratio of 1 to 1. That's all it tells you, which means that over on the product side, you get 1A and 1B, whatever charge they are. So you can't just assume that if AB is an ionic compound, that the charges are +1 and -1. You can assume that they are the same but opposite. If there's 1A and 1B in the compound, your assumption can only be that they have the same charge, same magnitude of charge, but opposite values. So +1, -1. They could also be +3, -3. And as long as they're balanced, it would take 1A + 3 and 1B - 3 to balance each other to form the compound AB. So how do you figure that out? Well, knowing what one of those two ions is oftentimes gives you a clue. So if you know if A happened to be aluminum, and it's an aluminum cation that's in the ionic compound, well, aluminum's always +3. Which means that the B, whatever the B was, must be -3. So there's certain cations you're supposed to know, like the alkalis, the alkali earths, silver, zinc, aluminum. You should always know what those charges are. And there's other ones that as well, but certainly my classes would have to memorize those groupings. And you should know that. The other one that you're going to see quite often is ammonium. And ammonium is always +1 as a polyatomic cation. The other thing that you should know is some of the anions, and you've got a table that has all the anions. So usually you're given a table, unless your teacher has made you memorize all the anions and their charges, which maybe I don't, but maybe you do. And if you've got that table or you've memorized it and it's in your head, you'll be able to recognize what that thing is, right? So if you know its charge because it's on a table, then you can use that to go back and kind of figure out what everything is supposed to be for the cation. Obviously, if I had a formula of A2B, then this, you'll get 2 A's for every B that is produced. And if B was -4, and there's one that's a -4, then the A's, because there's 2 of them, they had to be +2 each. So you need to figure that out. Don't just assume what the charges of the A and the B are, when you start talking about real compounds, don't just assume what they are. You have to really stop and think, okay, so what is that cation, what is that anion? I'm supposed to know what one of them is. I'm supposed to either know the cation, therefore I should figure out the charge of the anion, or I know the anion from the chart or my head or something else, and then I should be able to backtrack to get the cation. So, for example, if I see a compound that is Fe, well, let's go simple. If I see a compound that is FeNO3, well, I know that I'm getting a single Fe ion, and I'm getting 3 nitrate ions. But I know that nitrate as a polyatomic ion, because it's on the chart, and I've seen it so often that I just know that its charge is negative. Oops. I know its charge is -1. So because I've got 3 of those, I know the iron must be +3. Okay, so there are certain things we expect as teachers coming out of the solubility unit that you can do. Okay, and one is write a dissociation equation for an ionic compound. One other little twist about we expect you to know how to write the formula or the dissociation equation of an ionic compound. Let me give you kind of a weird one here. NH4HSO, whoops. Oh, sure, why not? Let's just go with that. That's fine. So NH4HSO3. So that, again, what type of compound is that? You should recognize ammonium, NH4. Anytime you see NH4 out on the left-hand side of a formula, you're talking about ammonium. This is an ionic compound. Ammonium, even though it's made out of nitrogens and hydrogens, which within that ion they bond covalently, the overall structure is a polyatomic cation, so it has a charge of +1. So it exists out there in the world as a cation. It bonds ionically to other negative ions. So NH4, in your brain, you've probably gotten pretty good at this point in your chemistry career, of kind of seeing that after the NH4, there's kind of an invisible division there. So the NH4 is the cation. That means no matter what you see over on the other side, on the right-hand side, no matter what you see, it has to be all clumped together into a single type of anion. It's not individual H ions and S ions and O ions or some kind of crazy thing. Even if you don't recognize what HSO3 is, and it doesn't just kind of pop into your head as, it's, okay, well, that's hydrogen sulfide. I know that. If you don't recognize it, but you do recognize the NH4, you have to say to yourself, well, I don't even know what it is, but it is the anion. And so don't try and separate these things. Whenever you're doing a dissociation equation, you get a cation and an anion. Now you might get multiples of them because they've got subscripts, and within the formula, that's the proportion. But there should be a single type of cation and a single type of anion, certainly for the things that we're doing here in Chem 12. Okay? So don't overthink it. So the NH4 is going to be the cation. And because it's ammonium, and I know that ammonium has a charge of +1, I write it down. I didn't put aqueous up there. I'll put aqueous here. Which means that whatever the HSO3 is, has to be the anion. Now, how do I know that the 3 that's on the HSO3, how do I know that 3 isn't standing for, well, you've got 3 of this polyatomic anion? If the 3 stood for, you've got this number of the polyatomic anion, you would have seen something like this, where the 3 was outside of a bracket, and it stood for, okay, here's the polyatomic ion inside of the brackets, and here's the subscript for how many of those things you have. Since there is no bracket around the HSO, that 3 must be part of the formula of the polyatomic anion. And so HSO3, it's like the bracket is actually there with a 1 outside of it. Now, no one ever writes that in ionic compound formulas, but that's kind of how your brain can think about it. And so that thing is the polyatomic anion, and the 3 belongs to the formula, which means that that has a charge of -1. Okay, so dissociations, being able to do a dissociation is really key, because if you get the wrong ions over here, the rest of this unit is going to be incredibly difficult because it's based on what do those things do. Okay, so dissociations are really kind of critical to all of this. So let me go back to where... So there is a general strategy to what you're going to do in this unit. Remember what the overall question is for this entire unit is going to be, when you take this compound and it hydrolyzes, will it produce an acidic, basic, or neutral solution? That's the general, overall, underlying, overlapping, umbrella question for the entire unit. Which means that ionic compounds dissociate first, and then you ask the very simple question, do the ions do anything? Very simple question. Do the ions do anything? So if I had the question, or if I had the compound AB dissociating in water 100% to form A plus ions and B minus ions, I then ask the question, does A plus do anything in water? Does A minus do anything in water? Does either of those ions hydrolyze? Does that hydrolyze? Does that hydrolyze? And I ask them separate, okay? Sometimes they'll even predominantly react with each other. We'll get that one. That one's kind of down the road. That's kind of weird. But the general question is, do either of them do anything? If the answer, like you kind of go through your head and say, okay, does A plus do anything? And you go through what you're going to see in next class. And the answer is no. And then B minus, does B minus do anything? Does it react with water? Does it do this? And you go through your mind all the things that it could possibly do. And the answer is no. If A plus does nothing and B minus do nothing, they then float around in the water doing nothing. Well, then the water is just doing what water does with its equilibrium, and the solution stays neutral. It's essentially, you're dissolving a compound into water and nothing happens. It's still just neutral water. Now it happens to have A plus and B minus floating around in it. So the bulk of this unit will be A plus, does it do anything in water? Trying to determine how you figure that out. What things do something and how do they do it? Do they act as an acid? Do they act as a base? So you kind of ask the question of that guy, does it act as an acid? Base? And then you go through the problem solving. You try and determine, well, how do I know if it's acting as an acid? How do I know if it's acting as a base? And if the answer to that question, or either of those questions, that the answer is no, then A plus does nothing. I then go on to ask the question, the B minus, does it act as an acid? Base. I literally ask the same question to each of the ions. And sometimes it's quite a complicated answer, whether it does or it doesn't, or the actual figuring out, what if you happen to have an ion that is amphiprotic and it can do both. There's B minus, there are anions out there that have an H that it can donate and a negative charge, so it could be a base. So maybe the answer is it could be both. Then you'd have to go on, well, which one does it do? Which one is it predominantly acting as? And so these questions can get quite a bit more complicated. But this is the general question. This is the general strategy that you're taking your ionic compound, you're dissociating it into its ions. Then you ask the question of each ion. Does it act as an acid? Does it act as a base? Figure that one out. Move on to the other one. Does it act as an acid? Does it act as a base? And once you've answered those questions, you can then move on. So let me give you a real example. Okay, keeping these I'm going to keep these questions here. Sodium acetate, or sodium ethanoate, if you're using the organic nomenclature. Okay, so asking the question. So the sodium acetate, you have solid crystals of sodium acetate, you throw them into some water, and you make a solution out of it. It dissociates 100% because it's a soluble compound because of the sodium. So it dissociates into sodium ions and acetate ions. Once you've got those two ions, you pick one. I mean, typically you'd start with the one on the left. I mean, why not? It doesn't matter which one you start with, but you go through the same process. So you start with the sodium and you ask the question, does it act as an acid? Does it act as a base? So the simple answers, or the simple next step question that you will take is, does it act as an acid? You can't act as an acid if you don't have a hydrogen to donate. Like literally, it's that simple. So by saying, does it act as an acid? You're kind of saying, does it have a donatable H? And sodium plus 1 does not have a donatable H. So it can't act as an acid. The answer to that question is no. Can it act as a base? Meaning, can it pick up a hydrogen from water? React with water, pick an H up from it, and form hydroxide. And to be able to do that, you have to understand the definition and how to identify different bases. One of the very critical things that we said is that things with negative charges can be bases. You notice we've never said positively charged things. Positively charged things have a really hard time of picking up more positive things off of another molecule. So if a sodium plus 1 bumped into a water molecule, it is highly unlikely that it's going to pick up another plus 1. Besides the fact that the sodium plus 1 means that it shed its outer shell electron and it's stable and it's really not looking to react at all. It's not looking to form any type of bond. So really, sodium plus 1 is doing nothing. It's not going to be an acid, not going to be a base. We call that when you do nothing and you sit back and you watch. Okay, so this is why I'm saying this. When you do nothing and you just sit back and watch, you are a spectator. And so the sodium is sitting back, not being an acid, not being a base. It is a spectator, just watching what's going on. Floating around, it's there, but it's not doing anything. So then we move on to the other one. We move on to acetate, and we ask the very same questions. Does it act as an acid? Meaning, does it have a donatable H? It doesn't have a donatable H. If you recall, and if you don't quite know this one, go back a couple of episodes, and I was talking about acetate and the structural nature of an acetate, being an organic ion. Those three H's, by where they've been written into the formula, those three H's are covalently bonded to the carbon, which means that a carbon-hydrogen bond is really non-polar. And so those three H's, because they're part of non-polar bonds, are not donatable. Only hydrogens that are in part of polar bonds are actually donatable in any appreciable form. So those are not, even though they're there, those are not donatable. They are not acidic hydrogens. So pretend they're not even there, which means there's no H's to donate on this thing. Okay, it has them, but they're not donatable. So this is not going to be an acid. Can it be a base? Well, it's got a negative charge, and I guess every single anion that dissolves into water, right, when an ionic compound dissociates, you're going to get an anion, every single one of them, by just the fact that they are defined by having a negative charge. That question is, well, they could be a base. And so the next thing that you say to yourself is, okay, it could be a base because it has a negative charge, but is it the conjugate of a strong acid? Because when it's the conjugate of a strong acid, let's go to Ka table for the 50 billionth time, those 6 ions down there, they are the conjugate of a strong acid. And when you're the conjugate of a strong acid, that means that you do not pick up an H to go back to the acid. 0% of the ions go back because 100% of the acids get rid of the H. So it's literally impossible for them to pick up a hydrogen. So if you are one of the 6 conjugates of a strong acid, you won't act as a base. If you're not one of those 6 conjugates of a strong acid, you will pick up an H and act as a base in water. This is not one of those 6. Acetate is not one of the 6 conjugates of a strong acid. Therefore, this thing will act as a base. That thing will act as a base. So we've determined that the sodium ions are going to be a spectator, do nothing, but we've also determined that the acetate ions are going to act as a base. And so when you take sodium acetate and dissolve it into water, the solution that results from that is going to be basic. So at 25 degrees, it'll be pH above 7. How basic it is, and this is kind of the difference between the qualitative analysis versus the quantitative analysis. How basic it is depends on how much you put into the water. Right? It depends on the initial concentration of the acetate, and then you'd have to go through the whole, write down the equilibrium of acetate acting as a base, an IRE table, Kb and K expression, go through the whole math, calculate the hydroxide, negative log that to get a POH, subtract it from 14 to get the pH. So the quantitative aspect of it is you need to know this to be able to figure out, okay, so you need to know like the mass that you dissolved into a certain volume of water to make this. And that may very well happen. I know in my classes, I have students, I might say, okay, you're going to make a solution of sodium, you're going to use sodium acetate crystals. I want you to make a solution that has a pH of 9. And so they need to work backwards to figure out what mass of sodium acetate do I need to dissolve to make my solution so that the pH is 9. And so you can do it. I'm not saying that you cannot do it. Your teachers may very well ask you to do the quantitative part of all of this, but it's not technically part of what you have to do in Chem 12. It's an interesting, good extension of the acid-base unit, and so a lot of us do it, but it's not absolutely necessary. So that is not going to be part of the videos right now. But if you wanted the pH, you would have to know a little bit more detail about how much sodium acetate you dissolved in the water, into what volume of water, so you could get the actual concentration and carry on with the calculation. Okay? But generally speaking, before we leave, generally speaking, the ionic compound dissociates. We're dealing with soluble ones, so they go 100%. 2, you always ask the question, does this act as an acid, does this act as a base? And you ask those questions of each of the cation and the anion, every single time. Now, it starts to go pretty quickly in your head, but it's those questions every single time that are going to be the foundation of the strategy you're going to use to determine if this is an acidic, basic, or neutral solution. And that will kind of play out in all the different examples we use over the next few classes. Okay, so that's the intro to hydrolysis. We'll see you next time when we start dealing with a way more detailed look at all the different ways that we can kind of trick you up and throw the different ions into there and make things a little bit more complicated for you. Okay, so we'll see you next time when we do that.